In this video, we're going to be looking at radioactivity, what it is, and writing the equations to represent it. Now, there are four main types of radioactive emission. So we'll be looking at those in detail. We're going to be looking at how they affect the nucleus, and we will be using nuclear notation to represent those four main types of emission. So first, just to quickly review the nucleus. The nucleus in this traditional form would contain protons and neutrons. In physics, we refer to those protons and neutrons as nucleons because they live in the nucleus. And we would place those here in this notation. This is referred to as the mass number in chemistry, but in physics, we call it the nucleon number. Secondly, the proton number can be identified here, or in chemistry you'd call it the atomic number, and this pretty much just gives you the properties of that element. It's fundamental to the element itself. By changing the number of protons in, you're changing all the characteristics of that element. So the proton number is important, and it's highlighted by placing it at the bottom of this notation. Isotopes are also important because isotopes maintain that integrity of the properties. They have the same number of protons, but an isotope of an element would have a different number of neutrons, thus maintaining the integrity of the properties, yet perhaps causing some radioactive characteristics. We'll look at why in a moment. But it's important to note that isotopes can be radioactive, and you would need to define the difference between two isotopes of the same element. So let's think about radioactivity and what it actually means. When we introduce the idea of radioactive emission, we're talking about particles, ionizing particles, or the emission of energy, and sometimes both. So the nucleus makes itself stable by releasing either energy and or ionizing particles. Now, why would a nucleus need to make itself stable? Well, the source of instability could be that the nucleus is simply too big. If we think of huge atoms like plutonium or certain isotopes of uranium, these nuclei are enormous, and that makes them unstable. The second reason why an atom might be unstable is not because of its sheer size, but because of the combination of protons and neutrons. There are certain combinations which are very unstable. So this should make you think of isotopes. This is an appropriate time to talk about isotopes because isotopes of some elements are radioactive, that means unstable, and some isotopes are not. And it's because of that proton and neutron combination. So before we look at these emissions in more detail, I'm going to introduce two new particles. So far, you are more than familiar with the proton, the neutron, and then the electron. But this is where things get weird, and I start introducing some new particles. The first one is the positron. The positron was discovered in 1932 and is the antimatter equivalent of the electron. So it's exactly the same as the electron, but positive in charge. The second particle I'm going to talk about is the neutrino. The neutrino was discovered in 1956 and has no charge and is 500,000, let me add a naught here, 500,000 times smaller than an electron, which is already 1,800 times smaller than a nucleon. So you can imagine how difficult to trace a neutrino might be. So those two particles, one being antimatter for an electron, and a neutrino, which also has actually an antimatter equivalent, which means it's exactly the same, but the antimatter equivalent. We will be discussing antimatter a little bit later, but for now, I just need you to consider that there's a lot more particles out there than the proton, the neutron, and the electron. And for now, we're going to focus on these two as well. So why am I bringing it up? Because I need to explain the four main types of radioactive decay. When a nucleus needs to become stable, right, go from being unstable to stable, it gets rid of something from its nucleus. And that could either be an alpha particle. An alpha particle is an extremely positive helium nuclei. Now, why is it a helium nuclei? Because basically it's a chunk of the nucleus. It's 4 nucleons. or 2 protons and 2 neutrons, which makes 4 nucleons. Because it has 2 protons and no electrons at all, it is extremely positive. It has 2 positive. So that is the quickest and easiest way to make a very big nucleus smaller. The second emission is the electron. Now you may ask, what on earth is an electron doing in the nucleus in the first place? Good question, but it is, and it leaves the nucleus at very, very high speeds because it definitely doesn't belong there. So that's the second emission, and it's called the beta emission. And then we have the anti-beta particle, or the positron. Now this particle is the antimatter equivalent of the electron, the positron. So sometimes something weird happens in the nucleus and an electron is released, but also on other occasions a positron is released, and we'll look at why a little bit later. But that's our third emission. Gamma is our fourth emission, and gamma is a wave. However, now you've looked at the photon, you'll understand why we can actually refer to gamma as a particle. It is a photon of very high frequency and so therefore high energy. Okay, so those are your 4 emissions. Now might be a good time to stop and take some notes. Now we're going to stop and look at these in detail. We have alpha decay. Alpha decay is when a nucleus loses an alpha particle and becomes a smaller and more stable nucleus. This is an equation representing that very event. We have plutonium, 240, that's its nucleon number, 94 is its proton number, and we place the nucleus before what we call the parent nucleus up here on this side, and then the arrow separates the fragments, the bits that come off, right? So the product of that reaction would be uranium-236, which is an isotope of uranium, has 92 protons, and the helium nucleus that's given off. And this is a nuclear equation. We write the name of the elements, and we write their proton number and their nucleon number, and they should balance. As you can see here, 236 plus 4 gives you 240, your original element. Now what I'm going to do now is do the same for beta and positron emission, and then we'll look more closely at what's actually happening in the nucleus for those 2. The beta particle emission looks like this. When a parent nucleus decays and becomes more stable by releasing a beta negative particle, it also releases an antineutrino, right? An antineutrino. How do we express that? Well, this is an example. We have radium-228. This is an isotope of radium, which is naturally radioactive, has a proton number of 88, decays, we show that with this arrow, to give off a beta negative emission, and we express that as a -1 charge here. So we would put this where we put the proton in order to balance those charges. The daughter nucleus, that's how we refer to as the fragment which comes out of that decay, the daughter nucleus, is actinium. And now we see something interesting because the proton number here is 89. This is bigger than 88. So radium had a proton number of 88, and now it has a proton number of 89, which is odd. But again, we'll look at that in a moment. And also an antineutrino is given off. Now in a physics IB question, you would not be required to learn the periodic table off by heart. So you would not need to find the value of this, this element. However, you do need to understand what's going on here. So as you can see, -1 represents the electron. 89 is the new nucleus, which balances out here, -1, 89, and 88. Sometimes in the antineutrino notation, you do sometimes see a 0, 0, because that would work out mathematically. It pretty much has no protons and no neutrons and no charge. This is beta plus decay, the positron. And similarly, we're going to see a parent nucleus which decays by releasing a positron, which we represent like this, 0 and a +1 here, and that gives us this daughter element of thorium, 230, and 90 is our proton number. And this time, what we get is a neutrino, not an antineutrino, but a neutrino. Okay, it's important that you remember that. You're going to have to learn this off by heart. That beta plus gives off a neutrino, and beta negative gives you a antineutrino. Okay, you have to learn that off by heart. But anyway, as you can see here, this nuclear equation balances out. You've got the parent nucleus on this side, has a mass number of 230 and a proton number of 91. And then here we have a positron emitted 0, 1, and daughter nucleus, which is 230 and 90. So this is your nuclear equation. Now, in terms of gamma, the situation is a little bit easier to understand because we're talking about a photon, and a photon has no charge, right? So we would simply represent an emission of energy in the following way. The parent nucleus and the daughter nucleus are unchanged physically, but energy is given off. You might ask how this can happen, how you can have this kind of conservation situation, but again, it is complicated, and we will come back to it. But the important thing is that you see that this gamma, this notation for gamma for a start, and that you have a 0 and a 0 to represent it in the equation. Now let's go back and look at that that beta positive and beta negative decay again, because that is probably the most complicated issue to deal with. So if we have a look again at beta negative, you can see here that something weird has happened to the number of protons, right? The number of protons has gone up. And that's basically why this electron was in the nucleus in the first place. Like, electrons don't belong in the nucleus. Why did it get there? Because something very, very strange happens. Beta negative is when a neutron becomes a proton. It mutates. Now, if we go back to the reasons for why something is radioactive, the second reason is that the combination of protons and neutrons makes the nucleus unstable. That's why it has to basically give something out. It has to change itself. So one of the ways that it will do that is by converting a neutron into a proton and making a more stable combination. Now, as a consequence of that change, we release an electron. We have a release of an electron and an antineutrino. And we can represent this as another equation, right? We have our neutron, which is nucleon number 1 and 0, becomes proton, a proton which we represent with the following notation, 1 and 1, gives off 0, -1, and then a neutrino, which is 0, 0, antineutrino, which is 0, 0. As you can see, this balances out. Okay, so this is a nuclear equation to represent what's going on inside the nucleus. Similarly, for beta positive, now this is where it gets a bit odd, because hang on a minute, a neutron becomes a proton. That insinuates that a neutron is slightly bigger, right, than a proton. But now we've got beta positive decay. And in beta positive decay, we have the opposite situation. We have protons becoming neutrons and then balancing out in that way. So there, the proton changes into a neutron, changes the nucleus arrangement, makes it more stable, and then releases a positron and a neutrino, right? And again, this is our notation. Proton is 1, 1. We have a neutron, which is 1, 0, plus 0, 1. You don't really need the plus there. I just put it there for emphasis. And then this time we have a neutrino, right? So this balances out. And you can see here, when we look at the beta plus decay equation, we can see that this also represents the change from a proton to a neutron. The number of protons has gone down. Okay, now this is weird because basically if neutrons are bigger than protons, why are protons now bigger than neutrons? Now this is something called mass defect, and this is something Einstein had a lot to say about, and this is where his E equals mc squared came from, but we'll talk about that next time.